All right, so for this third example of a third order equation, we're going to once again start off with our y of t being defined as e to the rt. And if you take the derivatives and substitute in, you end up with an r cubed plus 3r squared plus 3r plus 1 equals 0. And once again, you could either go to a graph. If you go to a graph, you will see that r equals -1 is a root of the equation. You can also kind of do something interesting, which is recognize this row from Pascal's triangle. And that has 1 for the first row, a set of rows for the second row, and then we sum the previous numbers to get the third row, and then sum the previous numbers to get the fourth row. And you'll notice that these coefficients are actually on Pascal's triangle. So that tells you that this is actually going to be an r plus 1 to the third power to give us that. So again, you can either see the graphing calculator tell you this, or you can just see it from recognizing a pattern. So now if we actually divide out the -1, as we always do, we're going to have our 1, 3, 3, 1. Bring down the 1 and multiply. Oops, sorry, that's not going to go there. It's a space. All right, and then we're going to multiply, so we'll have a -1. Adding up gives us 2. -1 times 2 gives us -2. Adding up gives us 1. Multiplying gives us -1. Remainder of 0, as we suspected. So that factors as an r plus 1 times r squared plus 2r plus 1 equals 0. And this is recognizable as r plus 1 times itself. So again, this is really r plus 1 cubed equals 0. So our r1 and our r2 and our r3 are all equal to -1. So to get our solution now, we need to make sure we have 3 linearly independent solutions. And so to build it, we're going to use the t's like we did before. We're going to have our y of t being a c1 e to the -t. Because of the repeat, we're going to have a c2 e, a c2 and a t, e to the -t. And now because it's third order, we're going to have a c3 t squared e to the -t. And again, these 3 terms here are all linearly independent. And so our general solution has that form there. And again, you could check that linear independence by finding the Wronskian and showing that it's not equal to 0. And you can prove that this is a solution by taking the first, second, and third derivatives, substituting into the original differential equation, and getting 0 as the result of that computation.